Cool. Hi. So yeah, we've been looking into the future of the carbon dioxide removal market. So the motivation for this project was really due to the increasing size of the carbon offset market at the moment, as companies and individuals want to offset their emissions. So this is only set to increase as well. The task force for scaling voluntary carbon markets estimates that by 2030, anywhere between 1.5 and 2 gigatons per year will be removed due to the market. So the issue at the moment is that a lot of the projects that are in the marketplace are of poor quality. There's a lot of questions around additionality and permanence. So CO2 that on paper is being avoided or removed isn't necessarily, which makes them essentially worthless. So there have been calls by the likes of Microsoft and Stripe for more projects that deliver more high quality carbon dioxide removal as opposed to offset. And so the purpose of this project is to visualize and investigate the cost and negative volumes of the different methods that we have available to us for carbon dioxide removal, both now and sort of projecting 15 years ahead. Most offsets at the moment are to do with sort of counterfactual, essentially. So they're looking at, for example, you have a renewable energy project. They're financing a renewable energy project or a improved forest management. The idea there being that the financing that comes from the offset allows these projects to go ahead, and therefore that wouldn't otherwise have been able to go ahead. So CDR doesn't have this problem with CO2 maybe not being removed because the carbon dioxide removal is happening physically, and it's being removed and stored. But there's still a lot of variance in the different types of CDR projects in terms of their permanence, and this is something that we went into a great deal of depth into investigating, and Jason will talk about later. Jenny.
All right. And so specifically, if we put some numbers on kind of the current and historic carbon offset markets in general, and so what here I am plotting data from a recently released, really interesting carbon offset database. So this is looking at the voluntary carbon markets. That's out of UC Berkeley. But there's three things that I'd like to highlight about kind of the historic trajectory of carbon offsets. One is dominated by emissions reductions, so not very little net carbon removal. Two, the offset issuance has risen significantly over the past decade, as we're looking at here on the left. So that's signaling increased demand. But three, those offsets are really cheap. And so the volume weighted average of all of these offsets in 2018 was $3.30 a ton. And so next slide. And while these dominantly emissions reductions offsets are very cheap, what we're looking at here is that higher quality offsets. So we're talking about emissions reductions that are associated with permanent storage like CCS from industrial sources, and then net carbon removal, they come with a price premium. And so they're being offered at and purchased at a significantly higher price. But that price premium, next slide, is also associated with a relative paucity in supply volume. So what we're looking at here on the left is that those higher average costs or prices that the removal or offset is being offered at are also associated with very low supply volumes. And so even if you want to if you want to pay a significant price premium for really permanent net carbon removal, the supply volume just isn't there right now. But the large caveat there is that when we're talking about these kind of medium to long-term permanent carbon removal options, we're talking about relatively nascent industries, and specifically many engineered solutions that are just beginning to scale. And so that means that kind of in the near term, and what we're looking at here on the right is data from Stripe request for proposals, looking at just the next 5 years. And what we see is that companies that are offering this long permanence net carbon removal are also projecting very high price reductions and increases in scale. So serious increases in the volume that they're able to offer over just the next 5 years. And so the question that we really wanted to dig into here is basically, is that going to be enough? Looking at trying to project forward in time, how fast will these prices fall? How fast will volume be able to spin up? And will that be able to meet demand? So I'll pass to Jason to dig into the data.
So concretely, what we did is we took each proposal submitted to Stripe by a specific company, and we plotted it on these two axes of kind of volume versus cost. We're going to color the companies as shown on the right there with different colors per industry. So for example, by the way, the goal is to get to this kind of like bottom right corner. So things that are as cheap as possible and can offer as high a volume as possible. You'll note on the x-axis, we only go out to 10 megatons here. Eventually, we're going to need to get to the kind of gigaton scale. So for example, here, Project Vesta is offering 200 tons at about $50. Charm Industrial is offering 10,000 tons at a much steeper price tag. And if we go through all the companies, we can just grab their offers in the year 2020 and plot them on these axes. It's kind of a lot going on here. So what we did is we just kind of reduced it to, which industry are the different companies coming from. So in the top left, we have sort of direct air capture DAC style solutions, quite permanent, quite high cost per ton, and unfortunately not much volume being offered, 10 or nearly 100 tons. As we move down to the bottom right, we see biomass and mineralization. Eventually, some of the cheapest tons on offer are soil, these orange points, and forestry credits in green. While it's great that they're kind of high volume and relatively lower cost, and they do seem to be kind of ahead of the game. A caveat here, an important caveat, is they're much less permanent. So whereas DAC might be sequestration for 1,000 or more years, forestry credits might not last nearly that long. So the first thing we wanted to do is project all these costs into a kind of a common basis so that they could be compared fairly. And to do that, we need to deal with the non-permanence. So here, just as a thought experiment, let's say you're willing to pay $500 for a ton sequestered via DAC. That would last for 1,000 years or more. If you were willing to pay that, how much would you be willing to pay for 1 ton sequestered via regenerative ag for only 15 years? Or in a more extreme example, how much would you be willing to pay for 1 ton of delayed forestry credits, which only lasts for a year? So you pay a farmer to harvest a tree 1 year later, or 1 ton of trees. How much would you be willing to pay for that? So to kind of grapple with this, what we did is we imagined you paid for a ton at year 0. We just wanted to plot like how much of it will be left over time. So with DAC, maybe it's left forever. With soil, maybe it decays with some time constant. With forestry, maybe that extreme example, after 1 year, the farmer harvests a tree and then all the carbon is gone. So to project these to a common basis, what we did is we decided to go with an exponential decay for leakage, so that every atom that you purchase has some constant probability of decaying or leaking that year. And then what we're going to do is we're going to say, let's calculate the synthetic cost of like a quote forever ton as the present value cost of all of the ton at time 0 plus all extra purchases you would need to make to replace any leakage. So what you need to do is buy it at year 0, 1 non-permanent ton. At year 1, you buy a fraction of a permanent ton. At year 2, you buy a fraction of a permanent ton, and so on, summed out to infinity. If we combine this with the fact that capital today costs more than capital in the future, so some cost of capital calculation, we get this fairly simple calculation on the top left, giving the price equivalent of a forever ton across any of these industries. And it's just an infinite series. Here we have the cost of capital and the permanence of the solution. So back to our old plot here. Here we have the sticker price of all of these. So the price that they're being offered to Stripe, even though they're non-permanent. If we adjust the price for permanence, we can see, so here's non-adjusted, adjusted, non-adjusted, adjusted. We can see that the soil solutions and the forestry solutions end up increasing in price as you would expect, as they're less permanent. This little right point here, non-adjusted is quite cheap, but because it's only 1 year worth, you have to buy 200 tons worth of it equivalently out to infinity. So the price is quite inflated. So when we take into account this cost of non-permanence, the cool thing is we can see soil is now kind of commensurate with these biomass approaches. Forestry, actually, a little surprising or surprised us, is still cheaper. So it's still pretty good, even if you have to pay to like replant all the forests that are burning every decade. Okay, so next thing we can do from the Stripe data is look at each company's own projections of its own future, which on the one hand are probably hopelessly optimistic. On the other hand, all we're going to try to do is plot it. There's a lot going on here. So eventually what we did is we just kind of came up with our own estimate of the aggregate of each industry. And I'm going to show that here. So here we have like all improved forestry management solutions, all soil and so on. We see this overall log linear relationship between cost and available supply. So the more expensive things these days are also more nascent. The supply available is smaller. Some of the cheaper approaches, we actually do have quite large supply available today. Finally, we can take this plot and transform it into an actual supply cost curve by just stacking the cheapest credits up to the most expensive, kind of from cheap to most expensive. And that looks like something like this. I'll pass off to Jim.
Brilliant. Well, John, I know we're running out of time, so I will go through this quickly. So this is our current state of affairs, what we're looking at, kind of carbon removal offerings in 2020. And what we see is that we're really dominated by our nature-based solutions. And so most of the supply, exactly as we saw before, supply is being provided by soils and forestry. And the one other thing that I want to emphasize is, remember that current cost of $3 a ton is off the scale. So everything is significantly more expensive. But projecting into the future, into 2025, not much has changed, it looks like, but the things to really realize is that x-axis is increased by a factor of 10. And so we're still dominated by our nature-based solutions, but we have basically a factor of 10 more volume. And if we go now to the end of the decade, so now we're in 2030, we've continued to grow. Our volumes are now above a gigaton of carbon removal on offer. And specifically, the important measures to compare to is that 1.5 to 2 gigatons per year of demand that was estimated by the Task Force on Scaling Voluntary Carbon Markets. And so what we see is that we're projecting that you can meet that demand, but the vast majority is going to be met by our nature-based solutions, somewhat less permanent, basic forestry and soils. And specifically to put that in a little bit more context, if I was to get my wallet out and pay for all this carbon removal, I need $33 billion to buy the cheapest 1.5 tons. If I want the next 1.5 gigatons, if I want the next 0.5 gigaton, I need to basically double that. So shell out 56 billion for 2 gigatons of our cheapest offsets. And then if I want to buy the whole shebangaboo, I need 100 billion to get. So I need another 50 billion to get to the last 0.5 gigaton specifically of pretty permanent carbon removal. But that's actually, guys, that's very cheap. And so $100 billion is less than 1% of current US GDP. So we can do this. And then finally, projecting past the end of the decade, we see that if you get past 2030, now our much more permanent engineered solutions are really starting to take off. And so we needed basically this decade to spin up basically the supply and get the cost down of our much more permanent engineered carbon removal solutions. And so this is basically our projection. I know I'm out of time. And so I think the one thing that I'd like to leave you with is kind of a realization that these are just projections. So this is working off, what we know today. One or more of those basic blocks that we see on the, cost supply curve could just completely go away if it turns out that removal pathway is no good. And so our real deliverable here is a now open source GitHub repository where you can basically access all this data, read more about our assumptions, implement your own assumptions, and then remake all of these visualizations and more. And that's all from us.